I think we can start, right?
Yep.
All right. Thanks for coming to the webinar. And today I'll be talking about, well, let's get real, RisingWave versus Flink, who's better? So in the past, well, I mean, if you check our webinars or probably check out blogs, we actually didn't really we haven't been talking about really this topic for a while because well, we are essentially these days a lot of things are going on, and the market is evolving super fast, right? And if you're familiar with the Kafka space, right? So there are acquisitions, and there are some service shutdown, and probably some new service just launched, right? A lot of things going on. But definitely, many of the users probably, I don't know, probably 30 or 40% of the users are actually asking us about, okay, how you compare with some other services like Flink or probably some other products like Flink or Spark Streaming or KCGDB or whatever, right? Yeah, definitely we have to answer, we have to answer these questions, right? How do you compare different services? So for today, I mean, I will probably not cover every single service in the stream processing market, right? But I can, we can just focus on two services, RisingWave and Flink, how they are different and how they are similar to each other, right? And in which time, and how do you choose between these two services, right? Two products, right? Yeah. So just get started. Okay. Well, I'm Jun Wu, and I'm a founder of RisingWave Labs, stream processing company. Before starting a company, I was at AWS Redshift as well as IBM Research at Modern. I've been working on the stream processing and database domains for 10 plus years. Yeah. Um, okay. And so let's talk about something about batch processing and stream processing, right? In the modern world, people really want to gain real-time insights from the streaming data, right? Just think about the real-time applications like, okay, stock market monitoring, inventory management, password tracking, web clicks, right? And all these kind of like applications really needs the real-time insights, right? You can always say that, okay, that insights could be, I mean, we probably don't really care about the real-time insights. Probably we can have the computation results or query results with a freshness of hours or days, right? For sure. I mean, if you want to do something like financial reporting or probably doing something like machine learning training, you can definitely do that. And there are pretty good systems like batch-based systems like Hadoop or Spark or Hive or Snowflake, Redshift, right? All these kind of systems can help you with the batch processing. As long as you don't really care about the real-time insights, you only need to have the freshness of hours or days. You can always use, I mean, Spark or Snowflake or these kind of services. And but the problem here is that well, in many use cases, well, essentially people really need to have real-time insights. For example, if you really want to do, let's say, stock trading, right? You only want to know, okay, you probably only care about what happened over the last 5 minutes, or probably only, oh, what happened over the last probably 10 minutes, right? And think about some other real-time applications like ride sharing, right? Essentially, if you call a taxi, you only care about what will happen for the next 10, probably 30 seconds, right? Or probably what happened over the last 30 seconds. So these applications really need to have, we really want to gain real-time insights from these applications, right? So if the all expectation of the data freshness is just seconds or minutes, then the batch processing systems such as Snowflake or Spark is probably are no longer the right choice. The reason here is that's what I just mentioned. These systems essentially batch load the data from the, I don't know, S3 or probably some upstream services, and then process the data in batches. Yeah, and this kind of processing style makes it unsuitable for supporting real-time applications. Then what we can do? So the answer is definitely stream processing. Stream processing, we have right now in the market, we have several great tool systems like RisingWave, like Flink, like KCDB, like Spark Streaming, and some others, right? When if you are familiar with the startup space, well, then probably there are probably 10 more. I don't know, probably 10 more different different products. But definitely, I believe that Flink and RisingWave and are among the two most popular systems in the stream processing world. So how do we compare these two different systems? How Flink and the RisingWave are different from each other? Okay, so before answering this question, let's just give a pretty high-level comparison of batch processing and stream processing and why stream processing is unique. For batch processing, well, stream processing is totally different from batch processing from at least two perspectives. The first one is that stream processing always perform the incremental computation, right? Where the batch processing involves the full computation. Let's say that if you have, let's say, a bag of data, right, or a PQUI file, then the best way to process it is to use a batch processing engine like Spark or probably Hadoop, right? But if your data is like streaming data, that comes one by one, like user behavior logs, right? Or probably some like click streams. You essentially want to process this data one by one and incrementally, right? Well, let's say that we want to compute how many the average price of the last ad bit, right? We don't really want to do the full computation. We can only we can just do the incremental computation as new event comes in. That's the incremental computation versus full computation. And second one, I actually have already mentioned, that is stream processing is event driven. Every time a new data comes in, every time a new event comes in, we will process it, right? Well, the batch processing is essentially triggered by the user for computation. Let's say that if you have a Redshift or if you have a Snowflake, then what people do is that they will issue the queries, right? Issue the queries and the query, okay, what's inside of the database and give me an answer, right? Let's say that we have if I have a Redshift and I have a bag of data, right, or a table, right? Then I can ask, okay, how many tuples are there, and what's the average price of the last probably of the last days, right? And this is definitely user triggered computation, right? So for stream processing is definitely not a new concept. Stream processing systems have already been investigated for, I think, essentially more than 20 years. And in early 2020, in early 2000s, academic researchers actually dived deep into the utilizing stream processing technology to facilitate real-time monitoring application. If you check out the papers for the first paper, essentially the first paper in the stream processing domain, which was published by professors in there are essentially two groups of people. Okay, one is one of them is other professors from MIT, Brown and universities, and the other group is from Stanford, and these two groups of researchers investigated okay, how the stream processing can facilitate monitoring applications, how we can do monitoring inside of the database, and with the emergence of the big data, right? Hadoop, everyone was talking about Hadoop in around 2004, right? Starting from 2004. People talk about, okay, whether we can do stream processing on top of big data, right? And that's why people invented systems like Storm, SAMSA, S4, and many others in order to build real-time dashboard or probably the real-time reporting requirements or probably just doing something like real-time ETL, right? As we enter the cloud era, And a lot of new systems just emerged, such as RisingWave, and in Python space, where there's a system called Quix, right? And also Bytewax, right? Well, these are Python in the Python space. They provide a Python API. But RisingWave provides for SQL, and Arroyo also provides SQL. Spec Streaming also provides for the SQL-like interface. All these systems emerged. And our goal is to enhance the stream processing systems by making them user-friendly and more compatible with the cloud environment. And that's why RisingWave and many other systems just emerged. So in this talk, we will compare again. Well, we focus on comparing Flink and the RisingWave because I believe that's where these are two of the most popular systems in today's stream processing area. Okay. And if you're not familiar with these two systems, I'm not sure whether it's your first time to heard of Flink or RisingWave, but even if you do have no idea about what stream processing is and no idea about what Flink or RisingWave is, no worries. You can just imagine that. I will assume that we are familiar with at least with some batch-based systems like Spark and Snowflake, right? For Spark, which is a batch processing framework, it's a computation layer on top of your S3 data, probably from your of your HDFS data. HDFS is definitely a file system data, distributed file system data, right? For Spark, it's a batch processing framework, while Snowflake is a data warehouse which contains both the computation layer and the storage layer, right? So you can imagine that Flink is essentially the stream process is essentially a counterpart of Spark's counterpart in the stream processing world, because it's a stream processing framework and it does not really store data. It do computations. It can do it provides all kinds of APIs. It's similar, very similar to Spark. I mean, in terms of the architecture, but the RisingWave is more similar to Snowflake. You can just imagine it like a counterpart in the stream processing world, because RisingWave has both the computation layer and the storage layer basically, and you interact with RisingWave using SQL. Similarly in Snowflake, where you interact with Snowflake using SQL, right? So again, to summarize, I mean, if you're not familiar with Flink and RisingWave, just think of it like how you compare Spark and Snowflake, right? Batch processing framework versus data warehouse. And for Flink and RisingWave, it's like stream processing framework versus streaming database, right? Okay. And then let's dive deep into compare these two different systems from different angles. The first one we'll talk about is application and use cases. And second one is the user interface. And third one is internal architecture. So for the applications and use cases, I have to say that since both Flink and RisingWave are stream processing systems, their use cases are kind of similar, right? Both of these systems focus on low latency applications or the applications that require fresh data. So think about the answer recommendation, network monitoring, stock dashboarding, travel booking, fraud detection, IoT computation. All these kind of applications require to process the real-time data, and potentially they really want to see the users really want to see the results with a fractions of seconds, right? Or even sub-seconds, right? But these systems are not very super good at, I mean, I have to say that it's not really good to do let's say financial reporting, because people probably do financial reporting every single month, right? I don't really think Flink or RisingWave are designed for doing that part, right? Well, probably, and they are not super good at doing machine learning training, right? Because for machine learning training, typically what people do is they probably train a batch of data of the last 1 year or probably last several years, right? It's not that good at doing that. But if you talk about high frequency trading, I mean, high frequency trading that definitely requires requires low latency. But if your high frequency trading application or high frequency trading service requires let's say microsecond latency, then I have to say that your RisingWave and Flink are not suitable for that. And in most of the trading firms are quants, right? So they essentially build their own system to achieve or even use they probably use C++ or Rust, or probably use FPGA, the hardware, right, to achieve the microsecond latency. RisingWave and Flink are not designed for processing achieving microsecond latency. So to come back to our topic, well, in terms of the application and use cases, both RisingWave and Flink are focused on use cases that require the low latency processing, and ideally the fraction should be like milliseconds to hours. Yeah, milliseconds, seconds, and probably minutes, right? 1 hour, I mean, you can use probably either stream processing system and or batch processing systems. I don't think there's a big difference. And so let's talk about two use cases, two typical use cases of Flink and RisingWave. The first one is streaming ETL, and second one is streaming analytics. Regarding streaming ETL, what is streaming ETL? Okay, so in streaming ETL, it's more like, okay, we have a bunch of data, right? We have streaming data from Kafka, Repanda, Pausa, or probably the database CDC from MySQL, Postgres, MongoDB, right? Or probably the batch data from S3, right? We essentially process the data in real time, do transformation, data enrichment, and then send the result into the downstreaming data warehouses or data lakes, right? Or probably some serving systems like Lakehouse, right? And for this use case, well, it's definitely streaming ETL. I mean, both RisingWave and Flink can support the real-time streaming ETL, meaning that they can send the data, do the computation in real time, and send the delivered result into downstreaming systems within low latency. And then what about the streaming analytics? Let's say that if you want to do monitoring, alerting, or automation, then for this kind of use cases, for RisingWave and Flink, RisingWave and Flink can both support for the streaming analytics, the monitoring, alerting, or automation applications. But know that, okay, we have to say that the architecture could be different. Your tech stack could be different. If you use Flink, because your Flink doesn't really store data, it's a computation engine. It does not really store data. So if you want to use Flink to do the streaming analytics, essentially you have to send the results into some serving systems like Redis, like Cassandra, like DynamoDB, or even Postgres, or probably MySQL, right? To send the result into these systems and use those and check the results in that system. You cannot directly check results in Flink because it doesn't really have the storage. You cannot do that. So you essentially have to dump the result into a serving system and query the data, or probably connect your BI tools to those databases in order to get results. But RisingWave is different from Flink in that it essentially have the storage. So you do not really need to have a separate Redis or Cassandra or a DynamoDB cluster. You do not need to have a separate Postgres to serve your applications. You only need to have one single system, which is RisingWave, because RisingWave can do both computation and the storage and the data persistence, and it can serve the ad hoc queries concurrently within millisecond latency. So yeah. So if you are familiar with, well, if you are using some BI tools like Superset, Metabase, Grafana, you can directly connect these systems with RisingWave. And one thing I want to highlight is that RisingWave is compatible with Postgres, and you can just use Postgres query language to process the Postgres-style SQL to query RisingWave data. And you just connect to you can connect to your superset, Metabase, and Grafana to RisingWave with RisingWave using the Postgres protocol. It's fully compatible, and you do not need to worry about whether you can work with your old data stack, right? You can do, but if you use Flink, then it's totally different story. You have to think about what kind of the data serving service you want to have, right? So that's a different part. So to summarize, well, I mean, so for both Flink and RisingWave can support for the streaming ETL, streaming analytics, and some other applications. But the different part here is that well, the RisingWave has its own native storage, which support the data persistence as well as low latency, highly concurrent serving. And the latency could be as low as a single digit millisecond. But for Flink, well, it's not working, and I mean it has to have a serving system in order to connect to your BI tools or probably connect to your applications, right? That's the difference. But both systems can deliver the results into downstreaming systems in such as what they, as I just mentioned, Snowflake, Redshift, all this, or probably Iceberg, right? So that's about the application and use cases. So, okay, and then let's talk about the user interface. Flink and RisingWave are having different interfaces. Flink, because it was built it was first building around I think it's around 2010. It essentially provides the MapReduce style API. If you are familiar with Hadoop, then I believe that you are also familiar with Flink because well, yeah, the API looks kind of like similar. I mean, essentially 15 years ago or 10 years ago, the first version of the API is very similar to the to Spark API, but the Hadoop API. But definitely the system evolved and now has a much better API compared to the easier to use API compared to 10 years ago. But it doesn't really change the fact that well, essentially Flink has provides for the MapReduce style API. And on top of that, essentially the underlying layer is essentially a stateful stream processing API. And the data stream API. And then on top of it, on top of the data stream API, it has the table API, which means that you can interact with Flink like okay, table style using table style API, right? And on top of table API, we have the SQL. And SQL is, well, I mean, Flink SQL is Flink style SQL. And if you check check his dialect, you will find that it's kind of like different from the some other systems. Well, it's different from PostgreSQL, it's different from MySQL SQL, it's different from Snowflake SQL. Yeah, so it's on its own the dialect, right? And so you probably have to learn. But for RisingWave is based on, I mean, the SQL language is based on Postgres. Basically, it's Postgres compatible, fully compatible with Postgres. And yeah, if you have any queries or Postgres queries, you can just run it in RisingWave in the same way. No, yeah, you don't need to basically translate from the Postgres SQL to RisingWave SQL. There's no such kind of transformation, and you can just use the same SQL language to query the RisingWave data. And essentially, you can also use the same tools, data management tools like dbeaver, right? I know that's super popular. And but people may sometimes people will ask us, well, okay, RisingWave is Postgres compatible, but a database problem, but a problem in modern database systems is that okay, SQL is kind of like limited for in terms of expressiveness, right? And probably I really want to use Python, and probably I really want to use, well, let's say the Java or some other languages, right? I have to say that you don't need to worry too much about that. And we actually support well, multiple language UDFs, such as Rust UDF, Python UDF, Java UDF, JavaScript UDF, C++ UDF, whatever UDF you want to have. No need to limit it to just a SQL, probably no need to just limit to Python, SQL, Java. Use any language you want in the UDF. And essentially, our UDF is different from the other UDF in that we also support a stateful UDF, which means that you can do stateful computations inside of UDF. This is super important in some of the domains such as financial services, because well, if you want to calculate the inventory management, if you want to do the inventory management, you essentially want to do some computations by the window closing time. So for that kind of computation, it should be stateful computation. It's not just stateless computation. It's stateful computation. You actually want to do computations on top of a batch of data, right? Probably last of 5 minutes data. If you want to do that using RisingWave's stateful UDF, and you can get correct results, and it's more powerful than any other UDFs. So to summarize, well, I mean, for Flink, well, it's great, right? And it has MapReduce style API, it has the data stream API, it has a table API, and on top of that, well, it has its own SQL language, right? But for RisingWave, it's totally different. It's Postgres compatible, and it has multiple language UDFs, right? Just to give you a sense of like what a code should look like. If you use Flink, then probably you use well the so-called you can submit a job, right? You can submit a job, right? So and then you can write something like, okay, data set equals to something, right? And then yeah, basically this is Java style, right? Well, I'm showing you a Java code, but definitely you can use for the Flink SQL, but for commercial, but essentially it is same, right? So it's basically a wrapper on top of the API. But for RisingWave, you just create material use. If you want to create, if you want to, let's say, build a data streaming pipeline, right? Or so-called the streaming job, right? Well, then the only thing you need to do is to create a material use. And if you don't really want to store data in RisingWave, people sometimes will ask, okay, whether I have to store data in RisingWave. No, you don't need to have to store data in RisingWave. You can essentially directly create a sink and sync data out. And the sink could be a streaming processing job. And RisingWave does not need to process, does not need to store your data. And okay, so there's some yeah, so okay, so yeah, we do support UDF. So UDF, yeah. So yeah, so basically that's a user-defined aggregation function, right? And we do support that. You can check our documentation. And okay, so one good thing of having Postgres compatible API, not API, it's not API, definitely not API. One good thing of being compatible with Postgres is that you can it essentially simplifies the way you build real-time applications. So let's say that in many complicated advanced use cases, you essentially want to have a long pipeline, right? You probably want to build an application on top of build a stream processing job on top of the results based on the results of another stream processing job, right? So if you want to use Flink, then the problem here is that Flink cannot, well, for Flink job, it cannot directly consume the results from the previous Flink job. You actually need to have a Kafka sitting in between two different Flink jobs. So essentially, your architecture will look like, okay, Flink plus Kafka plus Flink plus Kafka plus whatever you have, right? That's okay. That's good. That's good. Well, I mean, if you have Kafka, definitely you can reuse Kafka. But I have to say that well, from the cost saving perspective, it's definitely not that good because well, I mean, you actually have to pay two different services, and you actually need to maintain more stuffs, right? But for even if you are doing the self-service, right? I mean self-deployment, right? But for RisingWave, it's like okay, Postgres style, right? So you can just build a material view on top of material view, and you can check the terminology called cascading material view, also called a stacked material view. So that's because we can have material view built on top of another material view. You don't need to have Kafka sitting in between two different material views. RisingWave essentially uses S3 to persist your data to and so basically the downstreaming materialized views can consume the result can consume the data from the output streams from the upstream materialized views, which is super helpful. Okay. But that is not a stateful one, and that you can according to us. Yes, well, I mean, right now for the UDF, we only support for the JavaScript and the JavaScript. Yeah, yeah, I'm not sure which what kind of language will support for in RisingWave 2.0, but I can definitely check for you. But definitely right now we have already supported Python, probably JavaScript, and I can check what other languages we support. Yeah. Okay, so that's about the interface, right? And you can see that how Flink and RisingWave's interface is different from each other. And now let's talk about internal architecture. Many people will say that, okay, look, well, I use a service, right? So I use probably a cloud service. I don't really need to care about the internal architecture. But I have to say that for stream processing systems, the internal architecture could be very important, important because it matters. It does matter, and it affects many aspects. So for example, the execution performance, failure recovery, and elastic scaling. So think about, well, I mean, if you want to do multi-way joins or probably doing large window aggregations, then essentially the performance of running this kind of operators of this kind of queries totally depends on how we design the internal architecture. And similarly, think about the failure recovery, right? Let's say that, okay, one single node just crashed for whatever reason, right? Or probably it's just a womb, right? Auto memory, or probably just because, well, okay, the system just went down, right? Well, I mean, it definitely happens, right? Or if you're considering about the less scaling, right? Because for stream processing workloads, it essentially fluctuates, right? Whether we can scale in and out in real time, or probably whether we can scale in and out without shutting down the machine, or without the stopping word, right? If you care about the execution performance, if you care about the failure recovery, and if you care about the elastic scaling, you have to learn something about the internal architecture. I mean, you don't need to learn how to implement the internal architecture, but you have to understand, okay, how the system works and how the system can guarantee your execution performance and failure recovery and elastic scaling, right? So let's discuss that. And for internal architecture, I have to say that I mean, if I pick one, if we can only pick one aspect to discuss, that would be stateful management. Stateful management, state management. State management is so important because stream processing systems essentially continuously process for large volume streaming data, right? And if you want to process joins, aggregations, you essentially have to maintain the intermediate results for joins. For joins, well, I can discuss more about that. But for aggregations, it's essentially it probably could be a single tuple, right? But think about the windows. It could be let's say a 5-minute window, 6-minute, a 60-minute window, or in some big companies it could be 7 days window. If you want to maintain such kind of big windows or probably big joins states, you essentially need to maintain the internal states. And how to and essentially the state management mechanism guarantees for how we the state management mechanism guarantees how we persist the state and how we recover from failures and how we do executions, right? And okay, I have to say that so while the stream processing systems have already been studied for over 20 years, I have to say that most of stream processing systems built in the big data era could not support for stateful computation efficiently. I'm not talking about, okay, I'm not saying claiming that, okay, they cannot process it, well, they can do that, but they cannot support it efficiently. Just imagine that if you want to do, let's say, 10-way joins, or probably not to mention 10-way joins, probably just 5-way joins, run it in any big data system. So then you are immediately, without any tuning, then you will immediately find that it will crash immediately. So it's super simple to validate. You can try it out. Or probably you want to do, let's say, a 7-day window. Oh, 7-day window is probably pretty big, right? 1 hour window join. Then you immediately find that for some of the system where it essentially crash, right? Or in some cases, you will find that the system is getting slower and slower. The performance is getting slower and slower, and you have no idea what happened there. So I have to tell you that's what it's all about, the state management, how you manage the states. So let's talk about the joins. If you want to join two different data streams, let's say one is click stream and one is the impression stream, you join to these two streams, and after joining these two streams, you want to generate the tuple and generate results showing that okay, which impression leads to a click. Right. If you want to do these two-way joins, then what kind of states you want to maintain? You essentially need to maintain two hash tables in the state inside of the stream processing system, which is not transparent to you. Okay. Sorry, which is transparent to you do not need to manually maintain states, right? You can do that, but but it's kind of like transparent. But for the stream processing under the hood, it essentially maintains two different hash tables, two hash tables. One is the hash table for the impression stream, and the other one is the hash table for the click stream. Every time a new event comes in from the, let's say from the, let's say that well, every time a new event comes in from the, let's say the impression stream, it will essentially check the results, check whether there is a data, where's a match in the click stream, in the hash table for the click stream. If there's a match, then we will essentially make the result, right? That's how it works. And let's say that's where if a new event comes in from the click stream, similarly, we will check, okay, whether there's a match in the, hash table for the impression stream. If there's a match, then we send the output to a downstream system, right? That's how the stream processing system work, and that's why, that's how we use the states, right, for the computation. And but for stream processing, the challenge here is that sometimes for the stream workload can burst, right? Probably for the last 1 second, probably you have, let's say, 1,000 tuples, but for the next second, you probably have 2,000 tuples. It's kind of common, right? And let's say that if a state what if let's say the streaming workload burst, and essentially the hash table or the hash table size will grow, right? Definitely it will grow, and it grows too big, then essentially it can crash your machine, right? Because why? Because for the it's kind of easy to understand because for every single computer node, the memory size is kind of limited, or the storage size is kind of limited. If the state size grows too big, then probably it can crash your system, and that's why in many cases you find that okay the stream processing job gets slower and slower, right? That's what happens. So how to manage the internal state can matter a lot for your stream processing performance and for your failure recovery and the elastic scaling I will talk about later. Okay, so let's think about how Flink handles that. Flink actually essentially uses what what's a learning curve in RisingWave versus Flink? Well, I mean, there's no learning curve in RisingWave because RisingWave is Postgres compatible. So essentially, to learn RisingWave is similar to learning Postgres. Yeah, but for Flink, well, I mean, it's as you just mentioned. Well, I mean, it has its own API and its own SQL dialect. Well, so you probably have to learn something. Yeah, so let's talk about what the state management in Flink. Flink is MapReduce style, and it has a MapReduce style state management architecture, and which means that's where the storage is coupled with the compute, right? So let's say that which means that let's say that if I want to scale from one machine to three different machines, then what Flink will do is that it will split the states into three pieces and send the states into three different machines, right? For every single machine, it has its own state. It will manage its own state, right? That's how Flink works. Okay, so this ideally, it's reasonable and definitely it can work. But the problem here is that as long as you have, let's say, some distributed system background, then you will know that definitely the data can screw, right? Probably in this state, well, I mean, we have, let's say, 1,000 tuples, but 1,000 tuples. But in this state, but in this machine, we just probably have 10 tuples. That's the data screwness, right? That's not, that's inevitable, right? As long as you know, understandable that how big data works, all problem, and that's not inevitable. So the problem here of this architecture is that as long as the state grows, you will immediately find that probably some of the machines state will also grow and grow probably much bigger than the other machines because of the data screwness, right? And what will happen? So your system will crash, or probably your system will get slower and slower because of the OS paging, because of the so-called page swapping, right? Because you actually need to have to fetch the data from the persistent storage, which is much more slower than fetching data from the memory, right? So yeah, that's definitely challenging. But in RisingWave, we actually use a different architecture, which is called the so-called, I mean, we now here we call it a cloud native style architecture. Or more professionally, it's called a compute and storage decoupled architecture, meaning that in RisingWave, the state is essentially maintaining S3, while the computation is actually maintaining EC2, right? Where EC2 does the computation, while the state is in S3, right? Using this architecture, we don't. This architecture helps a lot in RisingWave because, well, I mean, as long as because well, you can imagine that for S3 there's no limit in S3, right? Well, there's no size limit in S3, so the state can grow as big as possible, right? Well, you don't need to worry too much about the memory or the memory or probably some other issues, right? So yeah, it can yeah, definitely you don't need to worry about the state management at all. So let's say that we want to scale from one machine to, let's say, 10 machines, right? What do you need to do in RisingWave? Essentially, the only thing we need to do is to, I mean, add more computer node. You don't need to worry about the state management at all, right? So which means, going back to the streaming drawing application. So essentially, RisingWave will put these two states into a S3 bucket, to a S3 bucket, so that people can just query so that's where people can just scale in and out, even if even if the workload burst, right? Nothing will happen, right? In this case. So yeah, to compare, I mean, RisingWave uses Flink uses the MapReduce style API, MapReduce style architecture, which means that its compute and storage are coupled together in the same machine. While RisingWave is using cloud native architecture, which decouples its compute from storage so that compute and storage can scale infinitely and independently. So yeah, let me quickly go through how the stream process how failure recovery how failure recovery can be handled in Flink and RisingWave. In Flink, because I just mentioned, well, essentially maintains a state in every single machine, right? In every single machine, while RisingWave maintains the state in remote storage, but it actually have the local cache in each machine. So if system crashes occurred, right? Let's say that one of your machine just crashed, then what Flink will do is that it will have to reload the checkpoint from your remote storage, right? That's what Flink will do. So that's where the failure recovery time is totally depends on I mean, the state size. Think about it, if you are doing let's say, multi-way joins or time windowing, right? Let's say 5-minute window and probably or even 1 hour window. The recovery time will be totally depend on your state size. But in RisingWave, it's totally different because, well, I mean, if a system crashes, look, in RisingWave, what we have is a cache in local machine. So essentially, even if a system crashes, well, no worries, we can just boot another machine and ask this machine to to access the data, to access the state from the S3. So in RisingWave, the failure recovery time is always second level recovery. No matter what happens, it's second level recovery, and it's not the recovery time is not correlated to the state size because it's always second level. So and that's failure recovery, and then let's talk about elastic scaling. So what if we want to scale from one machine to 3 different machines, right? Or in this case, from this one single node to 3 different nodes, what will happen? So in Flink, what will happen is that it will essentially have so this is essentially the process called state migration. It have to split the state into 3 different pieces and then migrate the state from this machine to 3 different machines. So in this case, we essentially have to, so the scaling time is totally depends on the state size, right? Well, let's say that we have a big state, then definitely it can probably take a longer time, right? Probably, I don't know, probably minutes or probably hours, totally depends on state size. But in RisingWave, again, I mean, if we don't really want this machine and we want to migrate this skill from this one single machine to 3 different machines, then it's always second level scaling, because we can always ask these 3 different machines to reload the states from the S3. So it's always second level instead of, let's say, instead of minutes or hours. Note that, well, I mean, we do not really require, RisingWave does not need to reload the entire state from S3 because, well, it's always cache, right? Basically, it's essentially a process of populating the cache. You don't need to have the cache fully populated, right, to execute the service, right? And for the first access, probably it could be slow, but well, it's always available, still available, which is super important, right? Because we don't really want to have any downtime in your service. You don't really want to have your service to be done for, let's say, hours or probably even 30 minutes. 30 minutes is definitely too long for financial services or probably logistics companies or probably ride sharing company. Too long. Yeah. So that's how state management is different between RisingWave and Flink. So how frequently is the state written to S3 in RisingWave? Okay, so the frequency is okay. So the write frequency is I mean, it's essentially tunable. I forgot the default number, but it's around 10 milliseconds to 100 milliseconds. So essentially, yeah, it's pretty short, right? And okay, one interesting thing I would like to mention is that RisingWave RisingWave 2.0, which will launch next week, essentially introduced a new concept called the local cache. I mean another caching layer. So basically here we will have another layer of cache called using EBS. EBS, yeah. So why we want to have this architecture? Because EBS will essentially help us to reduce the cost of accessing S3. Accessing S3, there's accessing S3 have 2 problems. The first one is that S3 latency could be, in some cases, could be 100 milliseconds or even 200 milliseconds, right? Let's say even though RisingWave has the local cache, I mean the local cache in local disk, right? In its local memory. But the problem here is that occasionally it still can, I mean, have the cache miss, right? So which means that it will have to access the S3. And another reason here is that I'm not sure, I mean, how often you guys about the S3. S3 actually charges you based on the actions, based on your put and get. So if you access S3 frequently, then you immediately find that your S3 bill price, S3 bill will increase drastically. And RisingWave this cache, the EBS cache, will significantly reduce the cost by 95%. By 95%, that's real. 95% reduction in the S3 cache S3 access. Yeah, is there a way to migrate Flink SQL to RisingWave interface? Okay, that's a pretty interesting question. So, these two different, we actually have a cheat sheet to help people to migrate from Flink to RisingWave, and essentially, recently we found that one interesting thing of ChatGPT is that it can essentially translate Flink SQL to RisingWave SQL, or Flink SQL to or even Postgres SQL or any other SQL, and you can also use that to translate from this, let's say MySQL to MySQL SQL to RisingWave SQL, or MySQL SQL to whatever SQL it is, right? ChatGPT is very good at that. But ChatGPT is not, well, let's say, I have to say that many people know that ChatGPT sometimes is not that accurate, right? We actually, in our documentation, we actually have a bot powered by Run LLM, which is a super cool AI startup. They actually have a chatbot for the chatbot, essentially the bot for the doc. And they actually can learn from our documentation and our code, and to help you write the RisingWave SQL. And it can also do some translations, which is pretty cool, and you guys should definitely check it out. Okay. Okay. So to summarize, well, I mean, in terms of I know that there are multiple questions in a channel. Well, I will answer later. Okay. So in terms of applications, well, RisingWave and Flink support both, well, I mean, streaming ETL and streaming analytics. But note that, okay, RisingWave SQL is more. RisingWave has its own storage, so that we can essentially persist. We can essentially persist the data, so that we do not need to have a separate serving system. And in terms of user interface, definitely we have a PostgreSQL and multiple language UDFs. And we use materialized views to represent the stream processing pipeline. Well, for Flink, right, it uses Flink job, right? And in terms of let's talk about the complex queries, workload burst, and no failures. I have no idea about how slow Flink could be. I mean, totally depends on state size, as just mentioned, right? These things are totally, I put a question mark because it totally depends on the state size. But for RisingWave, and it always runs smoothly, and instant scaling. We can do instant scaling and instant recovery. Okay, now let me answer a few questions. How do you compare the cost and performance between Flink and RisingWave? In many cases, well, I mean, people moved. Yes, we do have people move from Flink to RisingWave because of the cost. But essentially, we see many cases moving from Flink to RisingWave because Flink cannot work. For example, I mean, if you want to run multiple joins, then you will immediately find that Flink cannot sustain, and your system will getting slower and slower. But the RisingWave is more always at the same speed. So there's no performance degradation, and there's no node crash. But for Flink, if occurred, then it will crash, right? And if you really want to talk about the cost, we essentially have you can probably search for RisingWave versus Flink performance report. There used to be a report, but we are essentially building a new report. That report was built from last year, and we can probably later share the link to you. But we are working on a new report to compare the performance of Flink and RisingWave, just using standard, benchmark, no fancy stuffs. And essentially, in many cases, well, it can be. I mean, I have to always say that, okay, for the performance and cost, it always depends on your query complexity, right? Let's say that if you just want to run a filtering, right? For filtering or probably projection, super simple use case. Then I think that, well, I mean, same price, probably roughly the same. You can just write a Python script, right? Same size, same price. But if your query is complex, well, a little bit complex, let's to joins, then you will immediately find that RisingWave can be way more cost efficient than Flink. Could be, let's say, just have a, let's say 90% cost reduction. That's definitely possible. Yeah, totally depends on your, again, totally depends. I have to say that it totally depends on your query complexity. Can you perhaps still man the argument Flink?
4 minutes, King Jun, and a few more questions.
Okay, so let me answer this last question. So, where you do still recommend going for Flink? Okay, so so the number one reason people go for Flink instead of RisingWave is that Flink has the Java Java API, while RisingWave does not really have the Java API. We do have Java. We do have the because we are Postgres compatible, so we can definitely reuse the Postgres for their library, but in some cases, Flink does really want in some cases people really want to have the use Java, right? For example, it's a Java shop. Their company is a Java shop for sure. I mean, they will always go with Java, not SQL, and also probably Python, right? Or if it's a Python shop, then we do have Python SDK, which will be launched next week. But if you really want to have full Python experience, probably you can check out Flink. And there are some other systems like Quix, right? Or ByteRax. They are also pretty good. Well, they're essentially, probably they have even cleaner API because they are just built for Python stream processing. If you are looking for that, I would recommend checking out Quix. Yeah, we do have a pretty good relationship with Quix, and we always recommend their services. And yeah, and but for Flink, well, I mean, if you most of the queries can be expressed in SQL, then you're okay to use UDF for sure. I mean, I believe that we don't really see any reason people have to go for Flink if they want to use SQL. To be honest, very transparent. Yeah. All right. I think we are. I know that there are some other questions which I haven't answered yet, but I think the time is up, right?
Yes.
So yeah, if you have more questions, then feel free to join our Slack community, and we are always there, and you can just DM me or probably direct post the questions in the channel. Or again, in our documentation, there's an AI chatbot. You can always chat with AI if you're more interested in talking with AI, right? For sure. Yeah.
Thanks everyone. Bye.
All right. Thank you. Bye.